So our next speaker is Bhawna. She's from Chemistry Department of University of Delhi, New Delhi. She's going to talk about synergistic and nitrogen and fluorine codoping of tin oxide nanoparticles, revolutionizing photocatalysis, photocatalytic hydrogen generation and dye eradication. Go ahead, Bhawna.
A very good morning to all. I am Bhawna from Department of Chemistry, University of Delhi, India. Today I'm here to deliver my talk on synergistic NF codoping of SnO2 nanoparticles for photocatalytic water splitting and dye degradation. So, we all are aware of the environmental and global energy crisis due to increasing energy demands worldwide. But the non-renewable energy resources has led to implementation of some current global energy demands. They have drawbacks of that they cannot meet these energy demands as they lead to emissions of CO2 and other greenhouse gases. So we need to look for some other alternative sources of energy. And hydrogen as a syn fuel has been considered as a clean and sustainable source of renewable energy. My work is on hydrogen economy, and so far in the literature reported, steam electrolysis and coal gasification methods are associated with certain drawbacks of high temperature and pressure. So we need to look for some alternative sources of energy, and in my work, I'll be delivering solar energy-based photocatalytic water splitting. So in this photocatalytic water splitting method, we have thermochemical water splitting, which is associated with large solar concentrators to concentrate the solar energy. And hence it comes in the category of expensive instruments. Moving on to photobiological water splitting. In photobiological water splitting, enzymes are required to carry out the procedure, but the enzymes might be toxic sometimes and the yields are comparatively lower as compared to other reported methods. So I'll be selecting photocatalytic and photoelectrochemical water splitting methods for hydrogen generation. So basically, photocatalysis is the most sustainable approach to generate hydrogen gas through photocatalytic water splitting to deal with the energy crisis. Both the primary sources for this process are water and sunlight, and both of which are present abundantly. So there are no secondary pollutants, and it is a completely environmental friendly technique. Coming on to mechanism for photocatalytic water splitting. So basically, when the valence band of a semiconductor is irradiated with a band gap, which is irradiated with a light energy, which is equal to or greater than the band gap of the semiconductor, then the electrons are excited from valence band of the semiconductor to the conduction band. This leads to the formation of photo-generated holes and electrons in the valence and conduction band respectively. Finally, the photo-generated carriers are transferred to surface to carry out the reduction and oxidation processes to generate hydrogen and oxygen gases. So, the most essential requirement for a semiconductor to behave as a catalyst for photocatalytic water splitting is that the valence band of the semiconductor must be more positive than the oxidation potential of water to generate oxygen gas, and the conduction band must be more negative than the reduction potential of water to generate hydrogen gas. Literature have reported a number of metal oxides to be used as photocatalyst for water splitting methods, out of which TiO2 is the most common metal oxide known in this context, but it has a limitation that it can only absorb in the UV range of the visible spectrum, which limits its quantum efficiency. Then ZNO is associated with photocorrosion, and WO3 has lower energy conversion efficiency due to lower value of its conduction band. Then CO2 exhibits shorter half-life and hence faster deactivation. But SnO2 possesses all the essential requirements for a semiconductor to behave as a photocatalyst for photocatalytic water splitting. The most benefit of using SnO2 is that its band gap is tunable and it can be easily modified by several methods. In my work, I have preferred to choose anion co-doping of SnO2 because anion doping was increasing its band gap, that is the band gap absorption range was widened to absorb more of the visible light from the spectrum. It was quite easy to perform. It enlarged its lattice, which was causing disorderness and charge imbalance in the lattice of SnO2, due to which oxygen vacancies were created, which is an essential requirement in this photocatalytic hydrogen generation process. For this synthesis, I used the wet chemical method, which was fissile, air stable, and no carbon skeleton was involved in this method. So basically, I was having the precursor solutions of fluorine and nitrogen. I just prepared their methanolic solutions and were kept on stirring for 3 to 4 hours. After keeping them on stirring for 3 to 4 hours, they were several times washed with methanol solution, and finally, after hot air drying at approximately 70 degrees Celsius for 1 hour, white powdered substance was obtained. Coming on to characterization part, the very first one is the Libel fit of nitrogen fluorine co-doped SnO2. The powder XRD pattern actually depicts the rutile phase with tetragonal symmetry with the JCPDS file number 41:1445 with a space group of P42 MNM. The morphology and the elemental analysis was observed through SEM and TEM imaging. As we can see that the FE-SEM imaging, there are agglomeration of some spherical shaped nanoparticles, which shows the doping of nitrogen and fluorine onto the lattice of tin oxide. XPS analysis was performed to know the elemental composition and oxidation states of the various elements which were present in the lattice. After deconvoluting the fluorine 1s spectrum, 2 broad spectrum peaks were observed after using the Gaussian function, and these were representatives of the different oxidations of fluorine into the tin lattice. Similarly, nitrogen spectrum was deconvoluted into 4 peaks, which states that nitrogen was present in 4 oxidation states into the lattice of tin oxide. Coming on to oxygen 1s spectrum, we can see that there are 2 broad peaks in the oxygen 1s spectrum of nitrogen fluorine co-doped SnO2, which the one of the peak is associated with the lattice oxygen, while the another one is associated with the oxygen vacancies that has been created due to incorporation of nitrogen and fluorine in its lattice. Then the tin 3D spectrum represents that tin was present only in an oxidation state of +4 in this lattice. FTIR, BT, and Raman spectrum were carried out to know the bonding behavior, to know the hysteresis loop for the surface area, which was approximately 102.22 meters square per gram. And the Raman spectrum depicted the presence of oxygen vacancies, as we can see from the deconvoluted band spectrums. Coming on to the results, Actually, the results of hydrogen evolution were compared with pure SnO2 and with nitrogen-doped SnO2, and we can see from the graph that the hydrogen evolution rate was higher in the case of nitrogen-fluorine SnO2. Then to further enhance the efficiency of hydrogen evolution, we performed trial experiments with some scavengers and sacrificial agents and co-catalysts, and it was found that using a combination of EDTA and methanol as a scavenger and in the presence of nickel oxide, nitrogen and fluorine codoped SnO2 was giving 196.2 micromole per gram per hour hydrogen evolution rate. Since nitrogen-fluorine codoped SnO2 behaved as a photocatalyst for photocatalytic water splitting, so we tried another experiment of the same principle, and I performed dye degradation with certain dyes, and it was found that it could completely degrade methylene blue dye and 73 and 62% of methyl orange and crystal violet dyes. Thank you.
There's time for one or two questions. Yeah, if not, I have a question. If when you do this codoping, how do you make sure, or is it the 1:1 doping of nitrogen and fluorine?
Actually, the XPS analysis revealed that nitrogen had an incorporation of 4% in comparison to the SnO2 lattice, and fluorine was in 2% incorporation.
Thank you, Bhawna, for a talk. Nice talk. So please join me in thanking all these young scientists for brilliant talk, and we thoroughly enjoy that. Yeah.